All right. Super. Any questions from last time before I just do a quick review of what we talked about last time, and then we dive into finishing out rotations in 2D? Okay. So I would say that last time, a brief review, we want to understand the real world. And we know that there are symmetry transformations in the real world. So moving by translations, moving by rotations. Those are simple examples of symmetry transformations. We argued that symmetry transforms are a group, and in particular are a Lie group. So we have that the symmetry transformation that is parameterized by some parameters, real parameters theta A. There's some transformation associated with those parameters. That transformation is an element of a group. Because it's an element of a group, that means that there's a group multiplication law. So if I have a symmetry transformation by parameters theta B, followed by a symmetry transformation by parameters theta bar A, then that is the same thing as a symmetry transformation that is some function of the parameters theta B and theta bar A. It could be simple, like if I'm thinking about just translations, and I translate by 5 meters, then I translate by 8 meters, I just translate by 13 meters, just sum them. But they're more complicated functions, for example, when I have 2 rotations in 3D. That can be some complicated function of the 3 parameters to parameterize those 2 different rotations. Then we said that we want to do quantum mechanics. In quantum mechanics, the states live in a space, which is to say a complex vector space with an inner product, but in particular a complex vector space. We said that representations are a technical mathematical term that tells us how to take specifically a group element via some map pi as an operator acting on some complex vector space V. So we have, for some symmetry transformations, we have some map acting on the group element, which itself as an operator acts on some vector V. The V is an element of this complex vector space, and this pi is some element of GLV, the general linear group on the vector space V. Now, if we have that these representations are ordinary representations, then they completely respect the group multiplication rule. So if I take this group multiplication rule upstairs and I simply act with the representation, the map of the representation on that, so the representation of the group element T for the theta B parameters, followed by the representation of the group element associated with the theta bar A parameters, is exactly equal to the representation of the group element given by the group multiplication law. It's an ordinary representation. But because quantum mechanics is insensitive to overall phases, we have to allow a generalization, which is that we allow for a phase difference between the group multiplication law on the group elements and the multiplication law for the representations of the group elements. So we allow for what are known as projective representations or representations up to a phase. We said that Wigner's theorem tells us that symmetry transformations are affected by a linear and unitary operator or an antilinear and anti-unitary operator. For continuous transformations continuously connected to the identity, we know that this representation must be unitary. And irreducible representations are the building blocks of all representations. So our goal is to seek all the unitary irreducible representations of the Lie group of the symmetry transformations that we're interested in. Rotations being the canonical example. And ultimately, we will build up to rotations in 3 dimensions. So that's a brief review of last time, or the most important parts of last time. We also talked about, rotations in 2 dimensions. We abstracted to the ON and SON groups and had a discussion of the UN and SUN groups. So having perhaps brought this all back up to RAM for you, are there now any questions? Where if they're not questions, I'm a little worried that people are totally lost, because otherwise the other option is that everybody's completely on board. Which would be, yeah, great. So this is a different page, so I guess back here. But yeah, so here.
All right.
Yeah. And as always, this will all be thrown up as lecture notes on the comments for the 2 videos, or for the video for this lecture. questions on any of the material? Okay, we do have a fair bit to cover, so let me move ahead. All right, good. So continuing with SO2. Remember that the dimension of ON is the same as the dimension of SON, which you said was n times n minus 1 over 2. And then the dimension of UN is n squared, and the dimension of SUN is n squared minus 1. So simply doing a degree of freedom counting, we can see that for SO2, so the dimension of SO2 is equal to 1, and the dimension of U1 is also equal to 1. So it's not impossible to imagine that there's a connection between SO2 and U1. And in fact, there is those two groups, those two Lie groups are in fact isomorphic. So in SO2, we take the one real parameter theta to be an element of 0 to 2 pi. And that is mapped into a group element, which we said is cosine theta, sine theta, minus sine theta, cosine theta, acting on a 2 by 2, a two-dimensional vector in the fundamental representation or defining representation of SO2. And in U1, we again take theta is from 0 to 2 pi, and it goes to e to the minus I theta. And so there is then a bijection which takes us from this 2 by 2 matrix back and forth to this complex exponential. And so we have that SO2 is isomorphic to U1. And you can see this perhaps more explicitly. So I have x prime y prime is equal to cosine theta, sine theta, minus sine theta, cosine theta, acting on xy. And this tells me then that x prime is x cosine theta plus y sine theta. And y prime is minus x sine theta plus y cosine theta. And now let z equals x plus I y. Then z prime is e to the minus I theta z. Is e to the minus, well, let's write it this way. Cosine theta minus I sine theta, hitting x plus I y. And so then we get x cosine theta plus y sine theta plus I times minus x sine theta plus y cosine theta. So that explicitly shows how we can reconstruct or go between those two different defining representations. Let me just pause there for a moment. Yes.
If you like graphical memory for U1, what is like the physical transformation that we talk about? What has to be revalued with that?
Right. So, bang, sorry. So let me just pull it up here so that I don't make any mistakes. So So it's a set of all n by n complex matrices such that U dagger equals U inverse. That's one definition. And that's equivalent to the group of invertible linear operators that preserve the complex inner product. On an n-dimensional complex vector space. So in some sense, it's a natural generalization of the SONs, or really the ONs, which preserve the inner product on a real Euclidean vector space.
So I guess
Are you looking for, there's always a U to correspond to an SO?
No, I mean, I was just thinking about any like physical like transformations that are not.
You're going to have a hard time coming up with a defining symmetry transformation that's not going to be unitary in some sense, because we know that all symmetry transformations are Lie groups. And okay. Let me think about this for a second. Lorentz transformations are not unitary. Yeah. Good. Yeah. The reason why I could come up with that, the way that I came up with that, is that it's that only it's only for finite groups. It's only for compact groups that have unitary finite representations, finite dimensional representations. So you can come up with unitary representations for the Lorentz group, but they're infinite dimensional representations. So if you look at the 4x4 Lorentz representations, the defined representation, that's not going to cannot be unitary. Good. Other questions? Good. All right. So let's now compute all ordinary unitary irreducible representations of SO2 isomorphic to U1. We will come back to projective representations in a while. What should we expect? And I'm going to just lay out some mathematical theorems that I'm not going to prove. You can look them up if you want to prove them. I don't know personally that I have a good intuition for them, but they are very powerful, very important. So the first is Schur's lemma. So if a complex representation which is the map, and then the vector space is irreducible, then the only linear maps say M going from the vector space to itself, commuting with all the operators associated with all the group elements are lambda times the identity. Multiplication by a scalar. So this is a very restricting property for irreducible representations. And for us, the relevance is that one has a corollary. Forgive my spelling. If G is commutative, then all of its irreducible representations are one-dimensional. I believe I said last time or the time before that we're going to build up a lot of math and we're going to then apply it to SO2 first, and it's going to be a little bit of a letdown. This is the letdown, because all of the irreps are just one-dimensional. It's just a phase. But in the same sense, well, we'll get there when we get there. All right, very good. So we know what to expect. Let's now proceed. So consider a representation. Infinitesimally, and again, forgive my spelling, close to the identity. So we're thinking about the representation of some infinitesimally small rotation. So this is going to be equal to 1 plus, and I guess this is the 1 operator, plus I d theta j, and then plus order d theta squared. This is a one-dimensional representation. So we have one, or it's a one-dimensional Lie group. So we have one generator. We call that generator J. That J living in the group is just J, but when we look at the representation is an operator living, or an operator acting on a complex vector space. So now the J becomes an operator. So I'm going to give it a. Okay. So since rotations are symmetry, since rotations are a symmetry transformation, we know that this operator J is Hermitian. Okay. Further, we have the group multiplication rule. So pi on theta plus d theta must be equal to pi theta pi d theta, group multiplication rule. Right? The multiplication rule for rotations is just addition. The multiplication rule of operators is just going to be like so, operator, operator. Okay? And we just worked out what pi hat of d theta is. That was 1 plus I d theta j hat. But we also have on the left-hand side, because we're on a Lie group and we have calculus, we can take the Taylor expansion of the left-hand side. So this left-hand side is equal to pi hat theta plus d theta d pi hat d theta. So we can now, let's call this equation 1 and equation 2. Equate 1 and 2 order by order in d theta. So for d theta to the 0, we have pi hat theta equals pi hat theta. Doesn't tell us anything interesting. Order d theta to the 1. Now we have something interesting. Now we have I j hat. What have I done that is dumb? Theta. Theta. I have managed. Okay, good. All right, great. Notes are wrong in what I wrote, but I get the right answer because I have to. Great. So I have that d theta, or I have d pi hat d theta is equal to I j hat pi hat. Good. This is a sort of scary looking ODE, but what's the solution? Okay, you say it's trivial, so just tell me what it is.
E to the I j hat theta.
Yeah, perfect. How do you feel about that? Should feel pretty good. All right, great. So we know what's now worked, and this is, I hope that you are seeing a pattern, right? This is very similar to what we did for the representations of the momentum operator, right? That's another one-dimensional Lie group associated with a continuous symmetry transformation. So we're just doing the same trick again. And what I'll point out later on is that we can just use these tricks over and over and over again, completely general. All right, so we must work out the complex vector space acted on by pi hat, right? A representation is both the map and also the vector space. Okay, so clearly this j hat is a map from the vector space to itself. And further, if I look at the commutator of j hat with pi hat of theta, not theta hat, pi hat of theta, this is a commutator of j with e to the I theta j, that's going to have to be 0. Commutator of an operator with itself to any power is going to be 0. What does that mean? It means that this j operator commutes with every single element of the group.
Or the previous theorem.
Good. Well, the corollary we're on board with, that everything's one-dimensional. It certainly looks one-dimensional. But we also have that if you commute, the only linear map that commutes with all of the pi's is some scalar multiple of the identity. Okay, so by Schur's lemma, this j must be equal to lambda times the identity on any irrep. Now the lambda may be irrep dependent, and in fact it is irrep dependent. But what we can do is we can use this lambda to classify or to label our irreps. right? That j hat acting on some ket that lives in our irreducible representation, that's going to give me lambda acting on the ket, because j is just lambda times the identity. And so we'll then label our representations with a little subscript sub lambda. This is going to be e to the I theta j acting on lambda, which is, and this is a hat, e to the I theta lambda, lambda. Okay, good. So this is all that we can milk out of the local properties of our group. And when I say all that we can milk, I mean, it's somewhat in air quotes, because we basically got an enormous amount of information from this. But we haven't taken advantage of, or we haven't considered the global properties of this group. And it's topologically non-trivial, right? It's a circle, it wraps around onto itself, as opposed to like the real number line, which is topologically trivial. So globally, our Lie group manifold is a circle. I.e. rotation by theta and theta plus 2 pi must be the same. In the group of transformations. So hence, we have that. So to be very, very clear, let me make it a little bit more clear. So the transformation associated with rotations by 2 pi is the identity element in the group. And this has an important consequence then for our ordinary representations. So therefore, our pi lambda of, say, 2 pi plus theta, where I'm being, technically I should really write pi lambda of t of 2 pi plus theta, but I'm skipping the t for brevity. I'm sort of doing that somewhat on purpose to get you used to that kind of a notation. So this must be pi lambda of 2 pi, and then pi lambda of theta, which has to be equal to pi lambda of theta because the rotation by 2 pi is the identity. And the representation is a homomorphism. And a homomorphism takes identity from the group to the identity of the operators. What does that mean? So therefore, pi lambda of 2 pi, which is e to the I 2 pi, well, acting on a state lambda, e to the I 2 pi lambda lambda. And this has to be equal to just lambda.
That's,
Is that lambda lambda? Yes, but maybe, so I'm sorry, is this lambda the same as this lambda? Is that what you're asking?
no, just,
Which thing where? Okay, you got it. Great.
So I think it's just that. So what's left of the 2 pi? Is that a pi lambda or lambda? Where? Left of 2 pi. Yeah.
Oh, sorry. Yes. Yeah. No, I'm sorry. That's me being dumb. Thank you. Sorry. Yes. Good. All right. So what does this tell us? What must lambda be? Well, how does this restrict lambda? So e to the I 2 pi lambda has to equal to 1. What does it tell me about lambda? Can lambda be 1? Can lambda be 2? Okay, can lambda be a half? No. Can lambda be -1? All right, so okay, good. Okay. So lambda needs to be an integer. So we're going to have that J acting on the state M is M pi sub M theta. M is e to the I M theta M. And we've now classified all of our unitary irreducible ordinary representations SO2. Let me pause there. Bless you. I'm guessing this feels a little magical. And I would propose that as you do this more and more, it will feel more and more, or rather less and less magical. It will just feel ordinary. Let me pause for any last possible questions. Then let me yes.
Like, in the biggest, like, what are we trying to do here? I'm a little bit lost in the detail.
Sort of bigger picture, why are we doing this? Okay, that's a fair question. So I would say two related, very important reasons. We certainly know that we can set up experiments. And we certainly know that we can do things like move our experimental apparatus. And I would claim that we would not be able to claim that we understand the natural world if we were unable to make predictions for the results of experiments when the apparatus moves. Or alternatively, if, say, Tian makes a measurement, and Rachel, you make a measurement, and you two are a spatial translation away from each other, that Tian, after making his measurement, cannot tell you ahead of time, Rachel, what you will measure, and vice versa. Right? There's got to be a self-consistency to the physical understanding of the world, that there's one world, and the way that either of you would either measure or describe the world has to have some mapping between each other. So we would like to, well, okay, that's a statement. We believe that the physics of the very small is quantum mechanics. And so if there's some system that's quantum mechanical that Tian is trying to describe, then there better be some way that he can map that description into your way of describing the same quantum system. So how are we going to do that? What's the mathematics of doing that? And this is where Wigner's theorem comes in, which says that the mapping from Tian to you is a symmetry transformation, because it's just a continuous spatial transformation. So it's going to be some unitary linear operator acting on the Hilbert space. We would like to know what that unitary linear operator is. And the claim is that any symmetry transformation by Hilbert's fifth problem is a Lie group, is represented mathematically by a Lie group. And the name for the map from elements of a Lie group to operators in a complex vector space That's called a representation. Okay, so you seem on board with that, and we're happy with that. I don't want to stop. I kind of want to stop there because you're happy, but I don't want to stop there because the sort of corollary to this, which is amazing, is that after going through this whole procedure and simply requiring that the two of you are able to discuss the same physics and describe the same natural world, we have drastically restricted the types of mathematical structures that we can expect to represent nature, which, if mathematics has anything to do with nature itself, in some sense places a restriction on what nature can do. So you're never going to, if you have some kind of a 2D system, you're never going to have some kind of a irreducible representation that's more than one dimension. Certainly in terms of the ordinary representations, there's only discrete numbers of them. You cannot have a spin 1/2 or a spin 1/3 or so on and so forth. Now, we're going to go and talk about projective representations, and that's going to lift that restriction on the particular values of spin that a 2D object can have. But when we go to 3D, there is going to be a dramatic restriction on the types of spins that we can have. So that's, I would say, the two extremely compelling reasons why we're doing this. So we want to classify all of the unitary irreducible representations because those are going to be the fundamental building blocks of the quantum mechanics that we can use to describe nature. And if that is the description of nature, then those are the only things that nature can do. Great. A lot of questions. I'm just gonna, I think, Dorn, you're first, or I saw you first.
Two things.
Yes.
Firstly, so up until we made use of Schur's lemma, what we did was general
Any Lie group, any symmetry. Yes, this infinitesimal expansion around the identity. Yes, we're gonna exploit that over and over and over again. There are very few things we can do in math. There are very few things we can do in physics. And the great power of Lie groups is that there's an identity and there's calculus. And so we're just going to turn that crank over and over again.
Just wanted to clarify where the fact J comes.
I'm not sure I understand your question. So I've got a Lie group, and the Lie group is some manifold, and it's parameterized by some number of real numbers. In the case of SN2, it's one real number. And then there's the group generator. And the J is the group generator.
Okay, I was just checking.
I think maybe I'm going to talk more about that as we proceed, and maybe that will help with it. I'll come back to you. Yes.
Sorry, so just understanding our pi operator takes in the transformation.
Yes, it eats a transformation. It eats a group element.
Okay. So when we write down the pi of pi sub lambda 2 plus theta, is it implicit that there's a t of 2 plus 5 plus?
Yes,
theta?
that's what I'm saying over here.
Okay, so every time we write down transformation by that parameter,
Yes,
the thing goes into the operator.
absolutely. But what I'm saying is that the group element is synonymous with the parameters that describe that group element. So I'm just shorthanding, not writing the T.
There's no point in writing. Just a different way of writing.
It's a shorthand. Good.
Yeah, I just want to ask about, like, I understand what the pi is doing, but I want to ask about configuration J. I guess so.
Yeah, good. I'll come back to you.
John said up until we used Schur's lemma was general. Is Schur's lemma not general? Would you call it as
So Schur's lemma is general in the sense that the only linear maps commuting with all the pi's are the identity. But we're going to, for example, think about rotations in 3 dimensions. And then the generators, none of them commute with each other. It's only the j squared that commutes with everything. So the j squared will be a scalar multiple of the identity, but the j's will not be. The jx, the jy, the jz will not be.
That's why you just need to use J.
No?
Oh, I just.
Yeah, and we're doing rotations in 2D, so
I just mean you could have chosen any name like this J, but instead you just.
yeah, I kind of leading you on like a teacher. Yeah. Or maybe the J is for Jack. One or the other. Here. Okay, so I'm saying that this is some small real number. And so what is the, so just maybe just intuitively, what do you think the map for the identity element of the group, what do you think that maps to in the operators, the set of operators that act on public space? It's the identity operator. Very good. Mathematically, this pi hat is a group homomorphism, so it necessarily maps the identity to the identity. Okay, so if d theta is simply 0, so if I get rid of all of this, I better get the identity. So now the question is, what is my first order correction? First order in smallness in d theta. So it's going to be d theta multiplied by some operator. And because I'm a physicist, I scale out the I such that the operator that remains is Hermitian, because this is a symmetry transformation. And pi hat of, I need to have that pi hat dagger is pi hat inverse, because this thing is, by Wigner's theorem, it has to be unitary. And that means then that j hat is Hermitian, right? Because if I take the Hermitian conjugate this whole thing, take the Hermitian conjugate this whole thing, I get a minus I. And then I get the j hat dagger. And in order for pi hat inverse to be 1 to order d theta squared, I have to have that j hat dagger equals j hat. Maybe it's a homework problem for you. It's a quick one, just worth going through. And then I can have order d theta squared corrections, but I'm going only to order d theta. Does that fully give you an understanding of what I'm doing here? Okay, great. So this is now, I would say, the second time we've done this, because we did it before with the momentum operator. You did it for the position operator on the momentum basis. So maybe it's the third time you've taken a look at it. And the fact that it's still a little uncomfortable, totally normal. This is like, yeah, it took me a long time to just do this enough times that I'm like, okay, this is just what one always does. But good question, because we're going to do it again and again and again and again and again. All right, super. Other questions? All right, great. I think just in the nature of saving some time, I'll just make some statements and I won't write them down because they're sort of useful, but not that super useful. Or maybe I'll just write them very quickly. We'll blast through. All right, so let's examine. So 1, m equals 0. So we have here for m equals 0, any rotation by theta is mapped. Pi 0 theta is just the identity. This is a trivial representation. All group elements map the identity. 2, m equals 1. Same thing, r theta goes to pi 1. Theta is e to the I theta. So this is our defining representation. covers whole group once, and so therefore it's a faithful representation. So m equals -1, we get that it goes e to the minus I theta. So same as m equals 1, but rotates clockwise rather than counterclockwise. M equals 2, we get e to the 2I theta. And the group is covered twice. So only faithful are m equals ±1. I feel like that's pretty quick and easy. Great. Okay, so now let's take a moment and think about the potentially reducible representations. We said that every finite dimensional unitary representation is the direct sum of unitary irreducible representations. So thus a general unitary rep decomposes, well, general unitary rep of SO2, same thing as U1, on a Hilbert space, H decomposes the Hilbert space into a direct sum over subspaces labeled by M. So our Hilbert space H is H, say M1, and then direct sum H M2, direct sum da 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 da, direct sum M sub n, direct sum blah 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 blah. And a general rotation space is represented by pi of, say, some theta is e to the I m1 theta, e to the I m2 theta, da 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 da, e to the I mn theta. Everything else is 0. And the general spin operator is represented J hat is M1, M2, so on and so forth, down to Mn, so on and so forth. So it's really quite a simple matrix to manipulate. It's quite a simple vector space. This is very valuable for us. Also, maybe presaging quantum field theory or a modern way of thinking about this, what are the properties of a particle, or what does it mean to be a particle? I would say it means that there are certain properties that are invariant under symmetry transformations that if I turn my head to the side, this thing looks the same, in air quotes, as when I don't look to the side. And what that means quantum mechanically is that you don't have mixing of various components of your vector space. So where something you're more familiar with, SO3, the total spin of the particle is independent of how you may rotate your system. Now, the projection of that onto the z-axis will change. So you wouldn't say that something that's spin up is a different particle from something that's spin down. But something that's spin half is, in some irreducible way, different from something that's spin one. Because you can never, by a rotation, get out of that spin one subspace. You're never getting into a spin half or spin three halves or spin two subspace. So this is a way of classifying particles and the possible particles that can exist in our universe, or that we can represent by our mathematics, which is to say the types of particles that can exist in our system. Yeah.
Is J just the ending of the algebra form?
Is J just the element of the Lie algebra that generates the Lie group? Yes, we will get to that in excruciating detail later today. Good. Further questions? Okay. Let me say some words that I'm not going to write down, because it's sort of good to know. And if I had infinite time, I would love to go through it carefully, but I don't have infinite time. So the point is that we can use these M's, these MKETs, as basis states for decomposing any state. So we have, in general, so briefly, that if we have some psi of theta, which is the inner product of a theta eigenket of the theta operator hitting our state, abstract state psi, we can insert an identity which is summing over these various M states, which is then a sum over M of psi M theta M. And one can work out that the inner product of the theta and the M is itself an E to the minus I M theta. This should all look very familiar to you in terms of what we did for the momentum operator. And that familiarity should make sense in that one has, in general, the Peter-Weyl theorem, which says that the irreducible representations functions, right? So far we've been thinking about the one-dimensional vector spaces. Now we're going to think about the infinite dimensional vector space of all functions defined on a circle. That's a Hilbert space. And the claim is, what we said before, that Hilbert space decomposes into a direct sum of one-dimensional vector spaces, each associated with spin 0, spin 1, spin 2, so on and so forth, in the physicist way of things. But the mathematician's way of thinking about things is just an e to the I m theta. And those e to the I m thetas form a complete basis. So the irreducible representation functions form a complete basis. For the space of Lebesgue square integrable functions. Defined on the group manifold. Lebesgue, yeah. It's like a fancy Riemann integral. It's like it's a better Riemann integral that they teach you in very upper level math classes that very few people use. Good. Right, now, this shouldn't be a surprise to us because we know that the generators of our Lie groups are permission. And we know that our permission operators have eigenstates that form complete bases. And that's all that this is really saying. That we have some complete basis that is associated with the generator of our Lie group. And this is just a very, very general statement. Okay, something that I skimmed over is the determination of the measure for integrating over the group manifold. The technical terms that the technical term for the measure that one tends to use is the R measure, HAAR. There's some algorithmic way of constructing this measure. Because a Lie group has the differential structure, the way that one, I would say, more easily determines the measure is by doing the usual square root of the determinant of the pullback in a metric, which if you've done differential geometry, you're like, awesome, that's amazing, I know how to do that, it's great. If you've not done that, it's basically the usual things you've done for calculus, that if you're like integrating over a sphere, you're going to R squared sine theta or R dr d theta. Again, I will throw this up and you can take a look at it. Yes. Okay, good. Yeah. Other questions? Great. I guess what I want you to take away from this, in terms of this brief discussion about the measure, is that, you know, we do things like we have this integral d theta from 0 to 2 pi, integral d theta over 2 pi, and then we have the outer product of theta with theta, for example, for the identity, or when we are working with the real number line with the integral minus infinity to infinity of the outer product of x with x dx, or momentum with momentum outer product dp over 2 pi, that there's a well-defined way of algorithmically determining what those identities look like. It's not just, oh, that kind of makes sense, or oh, he just wrote that down and I'm just going to write it down, and therefore that's the answer. But there's a unique up to sort of basic things actual answer that you can get. All right. Yes.
So when we're talking about decomposing the Hilbert space to the direct sum subspace,
Yes.
we're requiring that it's finite dimensional reducible representations, which are the direct sum. So when we write the dot 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 in the decomposition and in the matrix, is it a finite matrix and finite direct sum?
Let me not answer that because I'm going to guess that it's going to be finite or countably infinite, and that there's some subtleties with infinite dimensional or uncountably infinite dimensional, but let me just check up on that.
So most.
Let me check up on it. Good. Other questions? Okay. All right. What do you think the representation of J operator is on the infinite dimensional vector space? What do you think the matrix element is? So if I were to compute theta j hat psi, or theta j hat, sorry, phi, theta and phi being two different angles that can take any continuous value between 0 and 2 pi. What do you suspect that this is going to look like from your experience with the momentum operator? Yeah. So certainly the theta phi is going to be a delta function. And so then this operator J, like the momentum operator, what do you think it's going to do?
But how do I do that here? And I'm as well as we.
So when we had this, what was this equal to? I'm sorry?
Eigenvalue x, or eigenvalue y times delta.
Now, if I had the x operator, which x and y are eigenstates of the x operator, I'm going to get an eigenvalue and then the Dirac delta.
Sorry, that's what.
Exactly. So this is I d by dx delta x minus y. Up to possibly a sign up front, but I believe that's correct. All right. So analogously, what do you think is going to happen here? So if I have the inner product of theta with phi is Dirac delta theta minus phi, and if I think about, say, the operator that gives me, that spits out the eigenvalues for which, or rather the operator for which these kets are eigenvalues, then this is going to be theta delta theta minus phi. But then this J operator, which is the generator of the translations in theta, where this P was the generator of the translations in position. What do you think this matrix element will look like? Exactly, the derivative, I d by d theta delta theta minus phi. And maybe I'll have you go through that in detail in the homework. So what do I need to do? I need to do generator is permission and matrix element generator. Good. Any other questions? These are good questions. Thank you.
Say,
Hmm.
so you said that, E is the momentum operator, is the generator for the completion, and J is the generator for the rotation. That's what makes it.
Angle.
Yeah.
So generators of rotation. Is it generator of rotations? Yeah, sure. Okay, I think that's actually a good sort of segue into what I want to talk about next. Okay, so recap, what did we do to compute the UIRs of SO2? We found the expansion of the irrep near the identity element. Taking advantage of the differential manifold properties of the Lie group. A complicated way of saying we can do calculus, we can take derivatives. And parenthetically, unitarity meant the linear term, the representation of the generator had to be Hermitian. And then we found our irreps to be an exponential, an exponentiation of this Hermitian operator. And the point is, this process of exponentiation is completely general. This exponentiation, I guess I should say, of the linear expansion of the unitary representation. Near the identity. Is a completely general procedure. For Lie groups. So from a general abstract mathematical point of view, the representation pi, or I guess the map of the representation, pi, is a map from the Lie group manifold of our symmetry transformation to the Lie group GLV, in which, as we talked about before, one takes the identity element from the group G into the identity element of the GLV group. So therefore, there's a one-to-one correspondence locally around the identity elements of G and G. Between the differential pi prime that takes vectors from the tangent space so the tangent space about the identity element of our group G to the tangent space about the identity element of the GLV group. Okay, and then pi itself is differentiable because we're considering continuous Lie groups. So it has a differential structure. Therefore, pi prime must exist. And it's pi prime that maps the vectors from the tangent space around the identity in the group to vectors in the tangent space around the identity of the general linear group. And generally, fully generally, we're able to reconstruct locally a manifold M at a point P from its tangent space at the point P. Just a second. So in our case, this reconstruction is effected by the exponential map. We thus have the following commutative diagram. Where we have our group G, for which we are seeking the maps pi that take us into the general linear group on some vector space B. Locally around the identity of G, we have the tangent space, and we can take elements from that tangent space down into the group through the exponential map. And then over here on the right-hand side, we also have the tangent space around the identity element of the GLV group. And we can take elements of that tangent space into the group by the exponential map. And we can take vectors from our tangent spaces using the differential map, pi prime. And so the last statement before I get to your question is this is what we want. We want this pi for the reasons that we talked about earlier. Figuring out this pi and classifying all the different pi's is hard. What's easy is to take advantage of the fact that this diagram is commutative, which means that we can go from the G up into its tangent space, over from the tangent space of the group to the tangent space of the general linear group, and down from the tangent space of the general linear group into the group GLV itself. That's what the commutative nature of this commutative diagram buys for us. And I've intentionally used a lot of technical differential geometric terminology. But I would like for you to see, at least in the big picture, sort of philosophy of what we've done so far with the momentum operator, the position operator, and most recently for rotations, that we've done all this technical mathematical stuff. We started with the group SO2. And we went up to the tangent space by expanding around the identity and understanding the properties of the generator J. That J is the vector that's hanging out in this tangent space. Then we found how that J looked on the tangent space around the GLV, right? We said it's just some number times the identity operator. And by some basic properties of the group. Well, okay, so good. So we found it's some number. Oh my gosh, I just erased everything. It's some number multiplying the identity operator. Then we exponentiated that to give us e to the I lambda j. E to the I theta j, which is acting on states lambda, which gave us e to the I theta lambda. Then we utilized the group multiplication property of the group, i.e. the topological properties group, to limit the possible values of lambda, right? So we were able to locally reconstruct the GLV from the exponential map, but that didn't necessarily tell us about the global structure. We didn't take into account the global structure, which we then did, which then quantized our spin for the ordinary representations. Okay, so that's the big picture. Please go ahead with your question. Yeah. Okay, so technically a tangent space. So technically, if I have a manifold, so think like a sphere, right? Because easy manifolds are, like Rn's, line, R2, R3, whatever. But there, everything's a little too easy. So think about a sphere, just the edge of the outer skin of a ball, which is like, just think about the skin of a beach ball. And I'd like to understand what a vector means on this beach ball. And the way mathematicians construct that is they think about all possible paths through any particular point on that sphere, and they look at the tangent vectors of those paths. So the path has some parameter that parameterizes the path, and I take the derivative with respect to that parameter. That gives me a vector. A vector, and the set of all of those vectors forms a vector space. That's what a tangent space is. And then in differential geometry, what you do is you spend a lot of your time trying to understand how to do calculus, multivariable calculus on these vectors, which is to say, how do I compare a vector in the tangent space here to a vector in a tangent space slightly an epsilon distance away? That's what calculus is asking us to do, comparing two things that are a slight distance away. And it becomes non-trivial when you have non-trivial curvature, because now a vector, say on the equator, if I transport it to the pole, it's kind of pointing in a different direction, versus if I take that vector and I transport it around the equator and then I bring it up to the North Pole, they're now pointing in two different directions. And the amount that that vector differs tells you about the curvature of that space. But there's this deep connection between this differential geometric way of thinking about manifolds and curvature vectors in Lie algebras and Lie groups. And it's in fact precisely the commutator of the Lie group operators, the generators of our Lie group transformations, that is identical to the curvature tensor, or it's related to the curvature tensor of differential manifolds. You're asking how these vectors compare to each other. If I say go around the little square. Yes, so I'm saying they are elements of the tangent space because they are, just technically. And because if you have the differential geometric background, this will create for you deep connections and insights. I imagine very few of you have that background, and that's fine. So I'm giving you these words as things to just have in your brain. The thing that I want you to take away as a sort of overarching understanding of the procedure that we're doing here is what I've mentioned here, that what we really want are these maps I that give us the unitary irreducible representations in the vector space. Because that's how we represent symmetry transformation quantum mechanically. And we found that that can place restrictions on the types of physics we can see. So we're deeply interested in these quantities here and algorithmically classifying them. And it turns out that the way to do this is to expand elements around the identity, the group elements around the identity, and consider the representations of the generators. So technically what we're doing is we're going up and then over and then down. So when we go up and over, we're finding the representations of the generators, and then we go down by exponentiating those to find then the representations of the group elements, which is what we sought to begin with. So that's the message I would like to take away. Even if all the differential geometry is like zoom over the head or just like, I don't care. So do you get the big picture?
So this is the recipe that will follow it generally.
Yes. Yeah. Yes. Yeah. Good. Yes.
I think I'm a bit confused by the concept of a irreducible representation. Like, how do we know that the representation how is irreducible?
Yeah, that's a great question. So what's the difference between reducible and irreducible? And this is something that I should have like a canned, excellent 30-second explanation for. And I'm struggling to come up with that. So can we park it for now? Yeah. But I'll make a note of it. Because I could give you like the technical, like an irreducible representation is one that's not reducible, but like, what is that? It's not very helpful. Yeah. Yeah, just in order. Don't apologize.
Okay. J, you said J was a thing, but I really.
Yes.
Is it both?
Well, okay, okay, good. So in here, it's a vector. Over here, it's an operator acting on a vector space.
Okay, yeah.
It's also a vector, right? Because I've got the vector space here, which is a manifold, and I have a tangent space to that, which is also a vector space. And so the operators live in the tangent space. So they're vectors in that tangent space, but they're also acting on vectors in the vector space. They're acting on vectors in the vector space.
So the operators.
I'm sorry, I did said something not quite right. So it's the vector. Okay. Not easy, not your fault. So let's be careful about our vector spaces, right? I've got the V vector space, which is the complex vector space where the states like live in quantum mechanics. So that's going to end up being a Hilbert space for us. It doesn't have to be for representation theory, but for us, it's going to be Hilbert space. And there are operators that act on that Hilbert space. So elements of this act on that vector space. So these will be operators. The generators of these general operators also act on the Hilbert space. So think about it this way, right? Like you've had some experience with SO3. So you've got the J squared operator, you've got the JX, the JY, the JZ. So you can ask on like a spin up half zero, I'm sorry, spin one half, spin up state represented by 1, 0, and the JZ operator is going to be 1, 0, 0, minus 1. So the JZ operator is an operator that acts on states in the Hilbert space, some 2 by 2 complex matrix. Now, a rotation by some angle about the z-axis acting on that 1, 0 space, 1, 0 state is going to be an e to the I theta JZ operator. It would be yet another 2 by 2 complex matrix, but different from the 1, 0, 0, 1, but it is an operator acting on the Hilbert space. So there's a lot of spaces floating around. So we'll try to be careful. So any element that's hanging out in here is an operator that acts on the vector space. Any element that's hanging out here is again an operator acting on the Hilbert space. Good. Anything that's hanging out here is a Lie group element. Anything that's hanging out here is a generator of a Lie group element.
And in that sense, okay, I understand. Because operators act on groups.
No, operators act on, we're thinking about operators in states, are acting on vectors in a complex Hilbert space, complex vector space.
They form a group.
So the GLVs form a group.
Yes.
Yes. And they will for us be a real group. So the parameters that describe a particular transformation, like moving by 5 meters, rotating by 23 degrees, those parameters are all real. So this Lie group manifold is real. So the vector space, that's the tangent space to this, is also real. So this will be a real vector space. This will be a real vector space. This will be, again, a real group whose elements act on a complex vector space.
Okay.
And it's kind of nutty. So what we've seen so far with SO2 is that the group is one-dimensional, it's a circle. Its representations are all one-dimensional. That's kind of nice, makes kind of sense, all right? But when we get to rotations in 3 dimensions, the group is 3-dimensional. But now we have a countably infinite number of different dimensional irreducible representations. We have a trivial representation, which is 1-dimensional, everything's mapped to the identity. We have the 2-dimensional spin 1/2 representation. We have the 3-dimensional spin 1 representation, which is the defining representation. We have the 4-dimensional representation for spin 3/2, so on and so forth. So there's even a lot of dimensions you need to keep track of in your brain at the same time.
Okay, just to capture the
Yeah.
point to which of those 4 objects J is a vector in, and which of the 4 objects J is an operator.
J is a vector in here. Pi prime of J is a vector in here. Pi prime of J is an operator here. Pi of an element G is an operator in here.
Okay.
You're welcome.
I think also like so for usable,
Representation.
yeah, is that more for like multiplied system that irreducible is like single?
Oh, great. Yes. So that's exactly the interpretation we're going to give to reducible representations, right? So we're going to think about the vector space that's being hit, the sort of vector subspace that is hit by this irreducible representation here, this block, as a particle with spin m1. And we'll think about the irreducible vector subspace, or the vector subspace that's hit by this irreducible representation here, as some particle that has spin m2, so on and so forth. Yeah, good. Okay. Further questions? Good. I think, so I hope that this is something that, while conceptually difficult, the goal is for it not to be difficult, but to hopefully make it clear what was actually being done in undergrad. Because I know that for myself, I was sort of given a bunch of just sort of rules to follow, and I felt like they all came out of thin air, and they didn't have a cohesive whole to me. And so what I want to do is I want to give you the background and the tools to understand this in full generality. All right, you're happy, that's good. Yeah, yeah. Okay, and for those who are skeptical, hopefully I will prove that this will be valuable to you as a soul enriching exercise. Okay, great. All right, so this commutative diagram tells us we may, for a general Lie group, follow the same procedure as for SO2 isomorphic TU1, which is to say, find the representations on a vector space V of the Lie algebra G of our group G. So I'm using intentionally the Fracture or Gothic font to distinguish the Lie algebra from the sort of normal font for the group. This is fairly standard practice. And exponentiate the reps, the irreps of the algebra. And there's locally a one-to-one correspondence between the identity elements of G and GLB and their tangent spaces. Okay, good. Good, good, good. And notice how global structure isn't necessarily preserved. By this procedure. Okay, good. So this is our motivation then to systematically understand Lie algebras. All right. So consider a connected Lie group. Since it's connected and it's a group, it must have the identity element, and every element in the group can be continuously taken to the identity. Okay, so so these are groups of transformations P of some theta A that are described by a finite set of real parameters. Theta A goes from 1 up to, say, n. Question. It means that there's a path fully contained within the group that goes from the identity to any element in the group. So SON is going to be connected, but ON is not connected because ON has the discrete symmetry that gives us a disconnected manifold. Okay, so the identity is no symmetry transformation whatsoever. But let's imagine I'm working in 3 dimensions and I want to rotate by about the z-axis by pi over 2 radians. So I can build up that rotation starting from the identity. So this is me, and I've done the identity transformation. I've done nothing. Now I start rotating by some d theta, another d theta, d theta, d theta, and I go all the way to pi over 2. So that was a continuous transformation from the group element of the identity to the group element of d theta, to the group element of 2d theta, to 3d theta, all the way up to theta is pi over 2. So that's what I mean by there's a path through the group parameter space connecting from the identities to the rotation by pi over 2. And that's true for any rotation in 3 dimensions. Great. Okay, good. All right, so I find a set of real parameters theta A from 1 to n, with each element of the group connected to the identity by a path within the group. The group multiplication law takes the form T theta bar A, T theta A. Well, let's call this perhaps BC is equal to T of FA of theta bar B theta C, with these FAs of the theta bar B's theta C, some real number, a set of n real functions of the 2 times n real parameters. Remember, I've got n real parameters theta C and n real parameters theta bar B. So this FA is a function of 2 times n parameters, and there are n of these functions. So I need n numbers to uniquely describe some element of, or to uniquely describe the transformation, which is some element of this Lie group. Okay, so taking so theta A is equal to 0 is equal to the identity element. We must have that FA of theta bar B of 0 is equal to F must be equal to theta bar B. Well, must be equal to theta bar A. And FA of 0 theta bar theta C must be equal to theta A. What do I mean by this? I'm saying what if I rotate by nothing, or I symmetry transform by nothing, then I symmetry transform by theta bar? Then my total transformation just has to be the transformation by theta bar. So that tells me this FA has to be the theta bar A. And similarly, if I do some symmetry transformation theta C followed by nothing, I better get back the symmetry transformation, which is just the transformation theta C. And so that means that FA of 0 theta C has to be A. Yes. It's like taking the inverse of T. No, I wouldn't think about it. I wouldn't. I mean, I guess you could think about T as a mapping from your parameter space into the group. So I guess so. Let's hold off on that for a moment. Okay. Yeah. Oh, it's just saying that it's some different set of parameters. So we could have written this as like theta A and phi B, but sort of the theta and theta bar emphasizes that both the thetas and the theta bars are coming from the same set of possible parameter values. This is, and if you want, this is notation consistent with the second chapter of Weinberg, Weinberg's field theory book. Okay. So by Wigner's theorem, these T theta A must be represented by unitary linear operators. U of T of theta, theta A. And we must therefore be able to expand. And in fact, it's unitary continuous, or rather continuous. Continuity being very important for what I'm going to do next, which is to take a derivative. So we must therefore be able to expand U of T of theta A near the identity. So U of T of theta A must be equal to 1 plus I theta A TA plus 1/2 theta B theta C TBC plus order theta cubed. I think I'm up to equation 3. Let's call these unitary operators, give them all hats. I think this should be an uncontroversial statement. I'm just doing a Taylor expansion of this U, where I'm expanding using the parameters of the expansion parameters. And whatever is multiplying those expansion parameters has to be an operator. And I'm just naming it a TA and a TBC. Now we're going to start understanding some properties of the operators. Theta B and theta C, these are just real numbers, so I can change the order freely. And so that tells me then that TBC must be equal to TCB. And by the unitarity, we have that T hat A dagger equals T hat A, which we said many times before. Great. So suppose that the U of T of theta A form an ordinary representation. And ordinary is opposed to projective. Then we have to have that U of T of theta bar B, U of T of theta C. This has to be equal to U of T of FA theta bar B theta C. Looking at you, Tian. How is this okay for you? All right, everybody else? I'm saying that this is my group multiplication property. And my group homomorphism, my representation has to respect completely this group multiplication property. There are no phases that come in. So I just take the U of this, the U of this, and the U of this, where I'm now using the U. Previously, I'd used the pi's. Now I'm using the U's.
Sorry.
Yes.
You said by unitarity, T is its own division bucket.
Yes.
But shouldn't it be this inverse division bucket or one?
The I. That's why I'm going to give it to you as a whole.
Oh, that's the I. Okay.
Good. And this is again where mathematicians differ from physicists, because a mathematician wouldn't pull the I out, and the mathematician would say that the operator is skew symmetric, where they would say that T dagger equals minus T, or let's call it T twiddle dagger is equal to minus T twiddle. We'll come back to that a bit later. Okay, let's expand. Let's call this, so 3, let's call this 4. To order theta cubed. Okay. So to do so, notice that this FA of theta bar B theta C, this thing has to be equal to theta bar B plus theta C plus an FABC theta bar B theta C plus order theta cubed. So I'm literally just saying this is a function, multivariable function of theta bar B and theta C. I know that about either 0 for theta or 0 for theta bar, I know what this has to look like. And so it has to be linear in the theta bar and the theta. And I'm unable, or it is not going to be a strict function of theta bar squared or theta squared, because this result is exact. And so the only second order piece has to be a combination of the theta bars and the thetas with some numbers that tell me how to combine them. That will be ultimately characteristic of the group. So these FABCs, because we're looking at a real group, these are real numbers. Okay, good. So now the right-hand side of 4 is u bar, sorry, u hat of t of fa of theta bar b theta c. So there's going to be some hairy index bookkeeping that we just need to keep track of, but it's not that bad. So this is u hat of t of theta bar b plus, theta bar a plus theta a. My gosh, what am I doing? These have all got to be a's. So I'm not trying to do anything fancy. Like there's got to be still a conservation of indices. Okay. Plus f a b c theta bar b theta c. And because these are all infinitesimal, we can expand. So this is going to be 1 plus, now what did we say? We said that in general, we have some u of some transformation, then we get I parameter and then operator TA, and then 2 parameters operator TBC. So we get plus I theta bar A plus theta A plus F A B C theta bar B theta C TA. That's our first order term from the expansion 3. And then we get the second order piece plus 1/2 theta bar B plus theta B plus F B D E theta bar D theta E, and then theta bar C plus theta C plus F C F G theta bar G, sorry, theta bar F theta G. And then from above, the TBC. And then plus order theta cubed. So I have, in air quotes, simply expanded the right-hand side here, utilizing the expansion of this FA to order theta cubed, and utilizing what I know the expansion of my group elements must be up to, again, order theta cubed self-consistently. And what I want to do is I want to compare that to the left-hand side, similarly expanded out to order theta cubed. So the left-hand side, if I look at this, so I'm going to get u of t of theta bar b, but u of t of theta bar b is going to be 1 plus I theta bar b tb plus 1/2 theta bar b theta bar c tbc.
But for the first, sorry,
So
the
take,
first term is with B in there. With the second, the third term, with maybe 3. But then you guys have different indices, you guys have
yes,
C.
yes. So each one of the operators themselves is going to be fully contracted with respect to the parameter indices, right? So I've got a 1, I got the full contraction here, I've got a full contraction here. So if I take this left-hand side and expand out both sides, at 1 plus I theta bar A TA plus 1/2 theta bar B theta bar C TBC. And you get the same thing for the thetas. theta cubed. And now what I need to do, or what I can do, is that this left-hand side has to be equal to the right-hand side, order by order in theta. So on the left-hand side, I've got a 1 times a 1, and that's equal to the 1 on the right-hand side. Okay. Now let's go to linear order. So I have I theta bar A TA times the identity on the left, and on the right, I have I theta bar I A TA on the right. I have 1 multiplying I theta D TD, and I have I theta A TA. I can just relabel A to D. Sorry, A to D. So to order theta 1 or theta bar to the 1, I have TA equals TA self-consistent. Great. Basically, I'm just saying that I've not learned anything. 1 is equal to 1, TA equals to TA. Great. That's good. If I work out to theta bar squared or theta squared, I'll get that TBC equals TBC. That's going to come from this term here, this term here, and then matching over on the left-hand side where I'm going to get a half, and then there's a half here. So that all works out. So the interesting thing is going to happen when I look at the mixed terms. All right. So to order theta bar theta, now we have something interesting happening. Because on the left-hand side, I have I, FABC, theta bar B, theta C, TA. And then I further have 1/2 theta bar B, theta C, TBC, and then another half theta B, theta bar C, TBC. I'm getting lost in my own indices, always terrifying. And I want to compare this to, okay, right, good, okay, good. So then I have plus another 1/2 theta bar C, theta B, TCB, but it's symmetric, so this will add, and that's my left-hand side here. Well, okay, trust me on this for now. And if I can compare to the right-hand side, I got the half theta bar. Oh my God, sorry, I got the I theta bar A, the I theta D. Good, and so this will be equal to minus theta bar A, theta D, TA, TD. Okay. I can drop all my various thetas, and this will tell me that the TBC is equal to minus TB TC plus, or rather minus I FABC TN. And then since TBC equals TCB self-consistently, well, we have a self-consistency relation. Right? So if I take this expression and I say that this must be equal to this, but also I can swap the C's and B's. So that tells me then that minus TBTC minus IFABCTA equals minus TCTB minus IFACBTA. And this should look nice and familiar. Because if I compare this term and this term, that looks like a commutator. And so therefore I have that the commutator of TB with TC, where all of these should have hats. This is equal to I CABCTA, where the CABC we define as FACB minus FABC is some real number. 2IFABCTA. And the CABC are known as the structure constants of the group. And the claim is that one can prove that locally you can fully generate the entire group just from the knowledge of the structure constants. Okay. So, i.e., all higher order terms three can be found in terms of the TAs and the CABCs. Cool. Question.
So these relations like when you got that,
These will be intimately related to the Clebsch-Gordon coefficients in the sense that so Clebsch-Gordon coefficients tell you how to perform a change of basis, where and I considered giving this as a homework problem. I may consider giving this as a homework problem in the future. The idea being, if I look at the direct product of two useful representations, say of rotation. So I've got like a spin half and a spin one. Then I can think of one natural set of basis vectors, which is the set of basis vectors which were the basis vectors of the original vector spaces. So 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. But it turns out that that gives you a reducible representation. That I would say more clever basis is to write this new vector space in terms of the irreducible representations. for which it naturally turns the full vector space into a direct sum, which would then be, in this case, the 1/2 representation or 3/2 representation. And so you could ask, how do I transform between those two different bases? One that I write in terms of a J1, M1, J2, M2, and another basis which is the J and M, the total J and the total M. Those inner products are going to be your Clebsch-Gordan coefficients. So that is specific to rotations SO3, the particular example that I gave. And SO3 is uniquely defined, as I mentioned, by the structure constants of SO3. And that's I epsilon I j k, right? You know, the commutator J I j j is I epsilon I j k j k. But this is going to be true more broadly speaking. So I could think about some other Lie group, trying to think of a sort of a non-trivial example. Certainly rotations in 2 dimensions are trivial because they're all 1-dimensional. So all of the reducible representations, or all of the sort of, yeah, all of the reducible representations are already in block diagonal form from the beginning. I'm trying to think about maybe, say, representations of the Poincare group. So I could think about having relativistic particles of, say, different spin, different velocities, and trying to think about the total state there. And then again, I would do a sort of Clebsch-Gordan-ishy thing. Yes. So there's going to be, I think maybe the short version, right? Coming back to your original question. So there is clearly a one-to-one-ish correspondence between the structure constants and the Clebsch-Gordan coefficients, because Clebsch-Gordan coefficients will depend on the group, the structure constants depend on the group, but they're not going to be identical. Good. That's where I wanted to get to. Yes, Tian, question.
Going from the structure constant to F A B C. All that.
Going from this is just defining, this is just a definition.
Yeah, we're going from the first one to
From here to here.
from
Here.
that one. From next page.
Previous here.
Right.
So
So
from this
yes,
line
from there to there.
Because presumably these are because these are antisymmetric. The F's are antisymmetric, which we should be able to see somewhere. Or did I claim that they were symmetric earlier and now I'm in deep trouble? No, I claimed that the T's were symmetric.
I just, when you swap the indices, there in the upper one, the one below.
Mm-hmm.
When you swap the indices, the sign stays the same. So wouldn't that tell you that it's
if these are symmetric, then I'm in trouble. Then these would all be zero.
zero?
Yeah. So I think I have, a little bit of homework myself to make sure that this is concluded in a nice way. I would like to say that you agree with me with this, in fact, this full statement here. Good, because that simply comes from here.
Yes.
So I need to convince you that this is true.
So you can't get from that line when you swap the signs. F, C to F, C. If you were saying from that line when you swap the initial exponential,
Yeah.
but you don't know that TBC. That line at the bottom of that.
Yes, I know what you mean.
You can't claim that if A and C is symmetric.
And it will turn out to be anti-symmetric. It's
Yeah.
very easy.
I don't know why that is symmetric, but
I need to remind myself. I've forgotten. I apologize. Good. I have run way over. Any last questions? Okay. Thank you very much.